Hello, everyone. Welcome to the lecture for Monday, September 14th on design and application of lasers at the University of Windsor. This lecture, I will be discussing Chapter 1, Introduction to Lasers. So, something I forgot to mention on Friday are my office hours. I forgot to ask, so in this class, we'll have to discuss when to hold office hours. Okay, so light in cavities. This introductory chapter is a very qualitative description of basics of lasers. Eventually we'll get to the math behind how they work, behind gain medium and pumping and rate equations and how cavities are designed and all these things. But I just want you to have kind of a general understanding of the setup of these lasers so that when we talk about these things, you're a bit more familiar about this. So we discussed this a little bit on Friday. So what lasers need are an energy source. So it's something to pump our gain medium. So these still can't violate the law of second law of thermodynamics. I remember I said on Friday that lasers were thought to actually be impossible before they were invented. And that's because people thought that they violated the second law of thermodynamics. But it turns out that obviously they don't because they exist. But they still do need an energy source. You can't just get laser light out of nothing. You still need to pump it with some energy. They actually tend to be fairly inefficient. A lot of them have wall plug efficiency, which is the amount of power that you take from, the wall, like outlet, to the amount of power that's delivered is somewhere between 1 to 10%. That tends to be about how efficient they are. So you need to have some kind of energy source, and I'll describe some of those sources in a second. You also need a gain medium. So the gain medium is what I was mainly focusing on Friday when I was talking about all these different kinds of lasers, how we had solid state lasers, we had gas lasers, we had liquid lasers or dye lasers. We had all these different kinds of laser types, like fiber lasers, all that stuff. That's going to be the gain medium. So it's whatever is absorbing that pump energy and converting it to the light energy that we want. It also needs a cavity. I put here, this is both the most important and least important part of a laser, which seems like a paradox. It turns out to be extremely important because you need to have feedback. So there's actually kind of a funny story about how the design of the cavity was first, how this design first came about. It turns out that the first people to design a laser, especially in the United States, who was Charles Towns, he had been working on the maser, which is microwave amplification by spontaneous emission of radiation first. So people had developed radar technology during the Second World War, and microwaves were very well understood, and radio waves. And so they understood how to create really, really strong radio sources and microwave sources so that they could pump molecules in the microwave region of the electromagnetic spectrum. But they couldn't get it to work in light, in the visible part of the spectrum yet. And so they weren't exactly sure how to do it. And then it turned out that at basically the same time, Gordon Gould came up with the idea at the same time as Charles Towns. And in fact, they had met at a conference shortly before they both came up with it. So it might be that they had actually discussed this before they patented it. But it turns out that patents back in the 50s were first to come up with the idea. You just had to have proof that you came up with the idea. It wasn't the first person to file for the patent. It wasn't the first person to get it working. And so Gordon Gould couldn't get a laser working, but he did come up with the idea. And when he came up with the idea, he was working like on a weekend in the lab, and he wrote it down in his lab book, and then he ran over to a convenience store that was located just off campus, and then actually got the convenience store clerk to sign his book saying, the date and time and all that stuff. And that was actually enough justification to show that he had came up with the idea first before Charles Towns, who had applied for the patent 3 months after that. But he didn't have any evidence that he'd come up with the idea before him. So this actually led to a very litigious, a lot of litigation, and some patent law that ended up lasting, some court cases that ended up lasting about 3 decades. It turned out that Gordon Gould couldn't actually get the first working laser because the United States government said that a laser was going to have military applications, and so it was top secret. So he wasn't allowed to work on this and wasn't supported by what was called ARPA at the time, which is now called DARPA, which was top secret government research in the United States. He couldn't work for them because it turned out he had ties to communism, and so in the 40s and early 50s, and so he couldn't work on these top secret projects because he had been deemed a communist. But then ironically ended up suing Bell Labs and AT&T and all these companies over the rights for the laser, ended up being awarded hundreds of millions of dollars. So ironically, although he had ties to communism, he ended up becoming extremely, extremely rich based on patent litigation, which I thought was kind of a funny story and kind of ironic. But anyways, in summary, a cavity is really important to get a laser to work because you need to have some kind of feedback. So, and that allows for coherence. The thing though is that it's also arguably the least important because there are a whole bunch of examples of lasers or coherent light that actually come not from having feedback in the system. So for example, we talked about on Friday, free electron lasers. So free electron lasers were designed with electrons that wiggle along due to magnetic fields, and then that wiggling ends up accelerating the electrons, and that causes this light. And it turns out that those don't need a cavity because the electrons don't bounce back and forth from a cavity or anything like that. You can also get coherent light from amplified spontaneous emission. So it's called semi-coherent. What it is that you have some molecule or atom or part of this gain medium that's being pumped, and it just spontaneously decays, and then from that a whole bunch, there's a cascading effect of this exponential gain that that this photon gets amplified. So that's without a cavity. You end up losing some coherence, so arguably for good coherence you do need this feedback. But there's another kind of type of laser called X-ray lasers, and this is when you pump it with a crazy amount of energy. Often it's like some kind of ionizing energy, and you rip out core electrons, and then X-rays are emitted as electrons fall down to some low-lying energy state. There aren't such thing as X-ray mirrors really, and you can't really have this in a laser cavity, and yet people still call these X-ray lasers. So there are a bunch of laser types that don't actually require cavities. However, for the first laser to ever work, they required cavities. So that's why I say it's both the most important and least important part of laser. Okay, so basic setup of lasers. What we have is, as I said, we have some kind of gain medium. So we'll go with a bright yellow light bulb. That will be our energy source. If I can draw a light bulb here, it's giving off tons of energy. We have this little light bulb. Okay, so this is giving it some energy. This energy source can be a light bulb. I can write this energy source. It can be another laser. Those are the kind of lasers that I work with that are pumped by actually other kinds of lasers. They can be a high voltage. And I'm sure there are other kinds that I'm blanking on right now. Okay, so then we also need to have a gain medium. So we need to have something that absorbs this. So this sends out, say, a bunch of yellow light, and this gets absorbed by our crystal. And so here we'll say gain medium. So this gain medium can be, say, a crystal. That's what I've drawn here. And that's for solid state lasers or, solids. You can have this as a liquid, as I said, for dye lasers. It can be a gas. So gas is one of the most common types of lasers. That was what I discussed the other day with argon ion. Those are useful for green. You can also get argon fluoride lasers. Those are for lithography, so for UV lasers. One of the most common types of lasers is actually called a HENI laser, helium neon, and those are what you guys have used in electromagnetic theory, or I guess the lab for electromagnetic waves. Also for your second year optics course, you have these little red lasers that come in these tubes, and those are called helium neon lasers, or HENI lasers for short. How those work is you pump it with a high voltage, and then the neon and helium collide to create this population inversion. Okay, so you get this gain medium that's absorbing all this light, and then you need some cavity, like some type of cavity. So that was a pretty bad mirror. So what you need is some kind of mirror. And this reflects back and forth all this red light. So you've pumped this thing with this light, and it's absorbed that, and now it emits this light in all directions. It doesn't know initially what it's doing. It just goes out in all directions. But then eventually some photon goes out in this direction and goes out in this direction. And this photon wiggles along, hits this mirror, bounces back, and comes back into the gain medium. Now, this crystal has to be designed in such a way that it absorbs the yellow light, but doesn't absorb the red light. Okay? And then, and again here, this light comes out, hits this mirror, and bounces back, and goes back into the gain medium. And it doesn't absorb the red light. And so that means that this red light starts bouncing back and forth preferentially, in this left and right direction, and not, transverse, so not outside of the crystal. And eventually what happens is that these photons that are going across in this preferential direction just get amplified and amplified and amplified, and all the other ones that spontaneously go in other directions, those don't get amplified, and in fact they start to diminish as this laser starts to work. And so eventually so many photons end up going back and forth in this direction that this is just going to be the dominant mechanism for all the photons, and eventually some of these leak out in that direction, say, and this is going to be your laser. So of course this takes some time, and so this will be part of the rate equation that we get to in the next few chapters. But this is the basics of what happens in a laser. Is eventually it reaches steady state. You have tons of photons that go in the direction of the cavity, and by tons I mean billions, quadrillions, quintillion kind of number of photons. And in fact, that'll be one of your upcoming assignments, is calculating the number of photons coming out of a laser. But there are tons of photons going in that preferential direction in the cavity, and almost no photons spontaneously being emitted in the other directions. And this is what allows a laser to work. Typically, these mirrors will be, will be highly reflective. So you have these two mirrors here. Oops. Reflectivity, which given by R, will be something like, say, 99 0.9% reflective. And this mirror here that actually, on the right, that actually allows the light out, this we'll call an output coupler. And that's because it allows light to leave the laser. And this reflectivity will typically be something along like 90%, something like that. It could be 99%, it could be 50%. I've worked with lasers that work both those ways. But it's going to be something like 90%. And so what that means is that if this reflectivity here is 90%, then what that means is that this amount of light that's coming out is really only 10%. And so yes, you think that seems kind of confusing at first, but yes, there's 10 times more light trapped inside that cavity than what's coming outside of that cavity. So whatever you see from that laser means it's going to be 10 times more light inside that laser than what you can see from your laser pointer or whatever you're doing. Okay, so we also get directionality. So your textbook has an equation, 1.2.1. I'll use a slightly modified version. The directionality for a laser beam, if you have a collimated laser beam, one that's going straight, we'll have a diameter of what's called 2 times W naught, or 2 times the radius, okay? And so, or the beam waist. So from here, this is W naught. It turns out there's a whole bunch of reasons you can think about this. One being the Heisenberg uncertainty principle. You can think about this as being that, you know, light is waves, that you can't have a Gaussian beam or a laser beam that's going to be infinitely wide. So it has to have some kind of width, but it turns out that if it has some kind of finite width, then it has some kind of finite divergence. And so this thing does slightly diverge after a while, and it turns out that this angle here, we approximate from when this is in the far field, we call that theta. This angle theta is equal to the wavelength over pi divided by that minimum radius, okay? Or if we want this to be also theta, such that this is 2 theta, and we can call that, say, I don't know, delta theta. Then delta theta is, of course, just twice that. Okay. So if you want to think about how fast these are diverging, you can think about, so if you look up into the night sky and you see a full-sized moon, how big is the moon, okay, compared to the whole sky? It turns out that the moon is about half a degree, okay? And it's more useful if you think about this in terms of radians, but that's 9 milliradians, or 9 times 10 to the minus 3 radians, okay? So what sort of beam radius do we need in order to have a beam when it's as far as the moon for it to occupy the same size? It turns out that if you rearrange that equation, then you get, and then this would be, you know, the size of the moon, gives you about 42 micrometers, or that's 42 times 10 to the negative 6 meters. So this laser beam doesn't have to be really big, and in fact, most, you know, pen lasers or something like that are going to be closer to about 1 millimeter. So in order to actually have a beam that diverges to the size of the moon, which isn't particularly big in the night sky, you need actually quite a small beam size at the beginning. So these laser beams are actually very directional. All right. The next comment on lasers is, or the laser light, is that they have really, they can have really long coherence length. Okay. So one of the reasons why I wanted you to discuss or wanted to understand Fourier transforms is for understanding coherence length. So if you have a function where you only have a single frequency, so say your E of t is equal to E naught cos omega naught t, I will call that omega 1 so that you don't get confused with the W naught from the previous, for the beam radius. So we have an amplitude, which is E naught, and we have this angular frequency of light. So if we look at this as a function of time, what we get is this thing oscillates as a function of time, and that has some amplitude of the electric field, which is E. But this thing oscillates forever and always because it's just cosine omega t. There's no other time dependence to this field. And so what that means is if you take the Fourier transform of this, so we write that with a curly f, we get the spectrum. And this is what I have you doing for that first assignment. So if we look at this, actually I should make this axis symmetric. What we get is omega 1 and negative omega 1. And this will be your answer that you get for these problems. So the coherence length is basically telling you how long this amplitude here stays constant. So it's the same here, it's the same here, it's the same here, it's the same here, it's the same here. Okay. And what we know from that being constant is that when you take the Fourier transform, this here is a delta function. If you haven't learned of delta functions before, you can ask me this in class, but delta functions are something that's infinitely narrow, basically. So these things are very, very narrow, and that's also going to be true for the negative frequency component. And so that is something that has an infinite coherence length. That means in the time axis, it's the same amplitude forever, and so it has an infinite coherence length or infinite coherence time, or in the frequency space, those frequency components are infinitely narrow. Now, that's not going to be true in general. In fact, that's not true experimentally at all. Some of them can be extremely long, but they'll always have some kind of width to them. And so this is the question from 1b, that this actually has some kind of width, okay? And that width then ends up giving you some sort of envelope, okay? And so this width here of these, of the spectrum is related, oops, to the width in the time dimension. And so that's question 2 of your homework, is understanding how those two things are related. But basically, the coherence length of laser light can be very, very long. It can be effectively thousands of kilometers or even millions of kilometers if you have, really, really good lasers. But it can also be extremely short. You can also make lasers that have coherence length of just a few microns. And so it depends on what the spectrum looks like, and that determines what this coherence length is. So your textbook talks about that they can have really large coherence lengths, but it's not necessarily true. It depends on the laser and how you have it set up. Okay, so something else I want to talk about is very basic light-matter interactions. And so your textbook has this drawing, and in fact, almost everybody draws these lasers this way, that you have an excited state, and we'll call this level 2, and we can have a ground state, and we can call this level 1. And we'll use the ket notation. So for those of you who have taken quantum mechanics, that's just telling us it's state 1 and state 2. And so what happens is that you have you've pumped to this. Here, I can use the colors from before. From level 1 to level 2, and then you have this laser light that comes out, and what you'd have to have is some photon from your feedback system, so from your laser cavity, that would de-excite this atom or molecule that you've excited from the ground state up to this excited state. It would tickle this atom, or would excite this atom in such a way that it wants to be de-excited, and then that releases its own photon. And so this comes down with a photon, and you already had your original photon. And so 2 photons are released. That's often how simple laser diagrams are drawn. It turns out this won't work. For those of you who have taken time-dependent perturbation theory, you'll know that if you have 2 states, what happens is instead you get, as a function of time, your population in state 2 goes up and then comes down, and then goes up and then comes down, and then goes up and then comes down. And it turns out that's because if you only have these 2 states, like I've drawn here, state 1 and state 2, you don't have yellow light and red light coming out. You, of course, have to have red light pumping this and red light coming down. And so you can't actually, on average, create population inversion. You can temporarily create population inversion. So you can have a more excited population up here, but then the next moment you'll be de-exciting that, because this is population's now at a maximum, you'll be de-exciting this and all that light will come out. And so you can temporarily have population inversion, but you can't permanently have population inversion. And so this doesn't reach a steady state. You can't have a steady laser this way. And so although these are drawn this way, you need to actually have more than 2 levels. And so what you need to do is, instead of having this drawn like this, what we would have is this yellow light would come up and pump to a higher level. So if you remember, yellow light is shorter wavelength than red light, or higher energy. And then something else happens where you excite this to some other state. And then some other kind of mechanism allows this energy to be released, collisions or thermal or something like that. And then it goes down to that state, and then you have this population inversion. And so eventually you'll have a whole bunch of atoms sitting up here, and they're just sitting up there waiting for something else to happen. And then you come in with 1 photon, and then all of these guys drop down, caused by that 1 photon. And so now you get a mess of photons coming out. These are all going to be generating photons. They'll all be clones of each other, and so they'll all have some kind of coherence. Okay? And so this gives you your laser gain. And so this, in this case, this is called a three-level laser. There's also a 4-level laser, and we'll be getting to this in a couple of weeks, where your 4th level is down here, and this has some other decaying mechanism. Basically, a 3-level laser has typically an excited state that's higher than that. It absorbs at a higher energy and then emits at a lower energy, and it absorbs at some state that's higher than the second state. 4-level lasers also has a ground state that has an even lower energy than that emitting state. You can have more levels, so you could have, say, another level here or another level up here, but basically you would just kind of like lump these kinds together so that it would still be a 3-level or 4-level laser. Also, monochromaticity is a bit of a misnomer. It talks about, in the book, it talks about laser light being monochromatic. It's not totally true, but I'll get to that in a second, more so maybe if I deal with modes in a cavity. So as I said, you have to have a mirror on one side and then you have a mirror on the other side. And so if this is highly reflecting, then what's going to be allowed in the cavity for this feedback to be happening is that the amplitude of the mode has to be 0 right at both mirrors. So this is 0 here, and then this electric field oscillates up and down until it's 0 at the other side. So for those of you who have taken quantum mechanics and you've seen particle in a box, it ends up being the exact same thing as particle in a box, right? And so what you have is your electric field. So this will say is the Z direction. Your electric field in the Z direction is going to be E naught sine K Z, right? Where this here is Z is equal to 0, and this here is Z is equal to L. If I could draw now. And so if you realize this, it has to follow the same properties as a particle in a box, in that this is going to be reflecting, and so it needs to be 0 there and there. Well, it's pinned to being 0 at those points, and so that means that this wavelength here has to be quantized. Okay, so it's the same thing as a particle in a box, and that it gives you quantized energies or quantized modes. So what that means is that sine kz has to be 0 at Z is equal to 0 and Z is equal to L. Well, sine kz at 0, I mean, at Z equals 0, I mean, that's always going to be 0. But at Z is equal to L, that's not always true. So that'll only be when kz is going to be n pi. Oops, this should be kl. Sorry. And so that means that k is going to be n pi over L. So that means our k, our momentum or our wave vector of our laser light is going to be quantized. Okay? So that means that since we have an electric field in Z and T is E naught sine kz minus omega t, and we just said that k is quantized, and in vacuum k is going to be equal to omega over c. If k is quantized, then that means that also omega is also going to be quantized, right? So that means that we only have certain frequencies that are allowed. So in omega, what this means is we have only certain frequencies that can be allowed for us to emit from our laser. Okay? Now, that's not the full story, because we also have this gain medium which only emits over certain frequencies. And so this is a monochromatic laser if our gain medium emits in a bandwidth that's only that wide. But we can also have gain media, I'll use purple, that can be very wide, okay? And this here be our amplitude of our electric field. So your textbook talks about light being monochromatic. It's true, but not completely in general. Some lasers are monochromatic, some lasers are not, and it depends on the kind of laser that you're working with. Okay, so for your daily assignment this week, I want you to understand what the energy levels come from. So what I mean by that is I've drawn here these energy levels, and these energy levels have to come from this gain medium here. And so this is some gain medium, and I'm just going to have you focus on if this were atoms or molecules, and describe to me what would be the source for these energy levels. So as we've drawn here, we have these quantized energy levels. So level 1, oops. So we have energy level 1, energy level 2. We even have, energy level 4 and energy, or 3 and energy level 0. What would be the source of these energy levels? This should be fairly straightforward for those of you who have taken some quantum mechanics, but for those of you in third year, this might be a little bit unfamiliar to you. So please feel free to ask me, feel free to ask your classmates, or post on the discussion forum if you're kind of at a loss, or if you're not sure if you're exactly on the right track. But I'd like you to kind of think about what these energy levels can come from, and how we can use those to describe these quantized energy levels. All right, and that is it for this lecture.